put them together to get a single value for this gamble. So the orthodox theory has an answer to this. It's called expected utility maximization. So let an act G just be an assignment of consequences to states of the world. For example, quitting your dull but stable job to work at a startup we can write it as in the state in which the startup fails, you merely scrape by. In the state in which you have low success, you have enough money but a long and boring workday, and so forth. And let's just say that sticking with your current job has, there's only one possible state of the world, you know what it is, as simplifying things, and it's you have enough money but a long and boring workday. Okay, so the orthodox view is that the value of a gamble is its expected utility value. That just means you take the probability of each state, multiply it by the utility you get in each state, add them together, and that's the value. I'll talk about what utility is in a minute. In fact, there are two different ways to think about what the orthodox view is. One view is that what you should do is perform the act with the highest expected utility value relative to your utilities and probabilities. The other way to think of this is, it turns out there are these theorems called representation theorems. They say that as long as your preferences satisfy certain axioms, you can be represented as having a utility function whose expectation you maximize. So on that view, the way to think of the orthodox view is that when a rational individual selects an act, he acts so that he has utilities and probabilities according to which that act has the highest expected utility value. So utilities are sort of roughly supposed to represent how good consequences are, how much you desire them, that sort of thing. But there are like two different views of how we get them. The first view is that there are these things that we have access to, they're in your head. You can say like, how much do you like wild success? How much do you hate a really boring workday? If you have that kind of view, then the first norm makes more sense. So you take the utility of each consequence and perform the act with the highest expected utility. The other view is that we actually don't really have access to these things. The main thing we have access to is our binary preferences. So for example, like I'd rather have extreme wealth and a short and joyous workday than have a boring workday. And then, and from that, we can sort of represent me as having certain utilities. So utilities come out of preferences rather than the other way around. So if you think of utility in that way, the norm's gonna be about, let your preferences obey the axioms. Okay, and we'll talk about that difference in a minute. So let's say we can assign utilities and probabilities to the various states of the world and the various consequences. Then, as you see on the graphs here, the expected utility value of each act is the area under the curve. In this choice, working at the startup has a higher expected utility than keeping your stable job. So you should work at the startup. And in fact, every rational person with your values and your beliefs or probabilities should work at the startup. And you can sort of see the way expected utility solves the aggregation problem is it says, okay, so there are 4 consequences. Say in this startup choice, you might get utility 1, you might get utility 4, you might get utility 6, or you might get utility 7. The value of each consequence is its utility value, and the weight it gets in your decision-making is its probability value. So how much does the fact that you might get utility 4 with probability 50% weight in your choice? Well, it weights 50%. Okay, so that's the basic theory. However, there are some problems that many people have identified. I'm not the first to identify these problems. The first problem is that, according to expected utility maximization, you can sort of have any preferences you want as long as they satisfy the axioms or as long as you maximize expected utility. That means that if you're risk averse in a certain sense, we still can capture you by an expectational utility function. So for example, let's say you're risk averse in the sense that you'd rather have $100 than a coin flip between $0 and $200. Then expected utility maximization says you're rational, but you have a particular utility function, namely the difference in value between $0 and $100 is more than the difference in value between $100 and $200, because that's what it takes for the $100 to have a higher expected utility than the coin flip between 0 and 200. And in general, if you're risk averse in the sense of you'd rather have some sure thing amount of money than a gamble whose mean monetary value is that amount of money, but whose outcomes are spread out, then you're going to be if you're an expected utility maximizer, you're going to have a utility function that diminishes marginally. So for each additional dollar, that's going to be worth less utility. Okay. So the first problem with expected utility maximization's view of what it is to be risk averse, namely having a diminishing marginal utility function, is that it looks like it conflates two different phenomena. Okay, so consider two people, both of whom would rather have one coffee cup than a coin flip between 0 and 2 coffee cups. Person one, just like a really jittery person, they can only handle 1 cup of coffee. Having 2 cups of coffee isn't any better than 1 cup of coffee because they would just have to pour the second one down the drain. So that person would rather have 1 coffee than a coin flip between 0 and 2 for kind of obvious reasons. 2 just really isn't that better than 1. Our second person, on the other hand, is like a voracious coffee drinker. He just wants more and more coffee. On the other hand, he has the following attitude towards gambling. He says, look, it's really important to me that no matter what happens, something good results. So it's just not worth it to me to trade away the certainty of getting 1 cup of coffee in exchange for the possibility of getting a second cup of coffee. Even though I like the second cup of coffee just as much as the first, I simply am not interested in taking the gamble that might end me up with no coffee. I'd rather guarantee myself 1 cup of coffee than take a coin flip. So both of these people will prefer 1 cup of coffee to a coin flip between 0 and 2. Therefore, according to expected utility maximization, they must have a utility function that diminishes marginally in coffee cups. It must be that the utility difference between 0 and 1 cup of coffee is greater than the utility difference between 1 and 2 cups of coffee. But intuitively, these guys have really different reasons for their preferences. And it would be nice if we could capture the 2 different attitudes. It seems like in the one case, the guy's utility function really is sort of like capturing what he values. He really doesn't like the second cup of coffee any much more than the first. But it doesn't seem like it's capturing the preferences of the second person. Now, on some views of the utility function, that's going to be a problem, particularly if the utility function is supposed to capture what the person desires, if it's supposed to capture some sort of like actual fact in the person's head or about their psychology. On the other hand, on some views of the utility function, this isn't going to be a problem at all, because the utility function just means that which represents preferences. These guys both have the same preferences. They both have the same utility function. Like, who cares if they would describe them in different ways or give different reasons for it? But even if we hold the second view, even if we think it sort of doesn't matter if the utility function corresponds to anything in someone's psychology or in someone's head, there are still going to be problems for this theory based on the fact that there are 2 different reasons somebody might not like a risky gamble. So this is a very popular example. It's called the Allais paradox. And this is an example that's supposed to show no matter what our view of the utility function is, there's some preferences that can't be captured by any utility function whose expectation we maximize. So how many people have seen this before? Raise your hand. Okay, not a lot of people, or maybe a lot of people have screens off. Okay, so first, let me offer you the following choice. I'm going to offer you a choice between two gambles. You could either have a 10% chance of $5 million and nothing otherwise, or you could have an 11% chance of $1 million and nothing otherwise. So just think to yourself what you would prefer. If you would prefer the first thing, a 10% chance of $5 million, raise your hand. Okay, if you would prefer the second thing, an 11% chance of $1 million, raise your hand. Okay, so forget that choice. Let me offer you a separate choice. L3 gives you an 89% chance of $1 million, a 10% chance of $5 million, and a 1% chance of nothing. L4 gives you $1 million. Okay, so think for a second about which of these two you'd rather have. How many people would prefer the first one, 89% chance of $1 million, 10% chance of $5 million, 1% chance of nothing? How many people would prefer just $1 million for sure? Okay, looks like very many hands. So the standard preferences in these examples are that people prefer L1 over L2 and prefer L4 over L3. But there's no utility function such that L1 has a higher expectation than L2 and L4 has a higher expectation than L3. So if you have these preferences, you're not an expected utility maximizer according to any possible utility function. And the intuitive reason that people have these preferences, it's like, okay, so you think about the choice between L1 and L2, and you say, well, they both have a minimum value of nothing. They're both very likely to get me nothing. But if I take L1, that 10% chance, I'll get $5 million. That's a lot higher than $1 million, even if I have a slightly higher chance of getting the $1 million. But when we compare L3 to L4, it seems like people prefer L4 because they say, look, the minimum value of L4 is $1 million. I get $1 million for sure. The minimum value of L3 is 0. That consideration just swamps any other considerations. And what that sort of reminds us is that expected utility maximization, while it takes into account the average value of a gamble, it tells you to prefer the average utility value, it can't take into account any sort of other values. For example, what we might call global properties. So for example, it can't be sensitive to what the minimum value of a gamble is or what the maximum value of a gamble is. It says, care about a gamble according to what its average value is. Okay, so here's my proposal. And to understand this proposal, let's just think for a second about what question decision theory is supposed to answer. So decision theory is a theory of means, ends, rationality. It's a theory that is supposed to tell you, if I want some stuff, and I want to know how to get it, what should I do? Now, means ends rationality is really easy when you're certain about what the world is like. For example, I want a beer, there's a beer in the fridge. What would be means ends rational would be to go to the fridge, open it, and take the beer. But it's actually trickier to say what it is to be means ends rational if we don't know how the world is going to turn out. And in fact, just knowing the values of various states of the world and how likely each act is to lead to these consequences, this still isn't going to answer the aggregation question. This is going to leave the aggregation question. We're not going to have enough information yet to answer it. Okay, so I mentioned earlier the way expected utility sort of thinks about the value of a gamble. Here's another way to think about what expected utility is saying. So this is just sort of reconceptualizing what the theory is saying. So in this startup gamble, there are 4 considerations. Here's one consideration. No matter what, you'll get something worth utility 1. Here's a second consideration. With probability 0.8, you'll get an additional utility of 3. In other words, in the top 80% of states, you'll get an additional utility value of 3. In the top 30% of states, you'll get beyond that, you'll get an additional utility value of 2. And finally, in the top 1% of states, you'll get an additional utility value of 1. So those are the 4 considerations. Expected utility maximization says, what's the value of each consideration? Its probability. But you might think that that is, in fact, I think that that is too strict, because people might value these considerations in different ways. For example, I might be the kind of person that says, I care very much for what's guaranteed, but stuff that's not guaranteed, stuff that I only get in, say, the top 80% of states, that's worth something to me, but it's not worth as much. Maybe, for example, it gets weight 0.6. Stuff that I only get in the top 30% of states, that's worth something, but that's worth proportionally even less to me. So maybe it just gets weight like 0.1 in my deliberation. And stuff that I only get in the top 1% of states, that's worth very little to me. Maybe it only has, it gets weight 0.001 in my deliberations. So I would be represented by this graph on the left here. I would sort of shrink the value of these considerations relative to their probability, and I would shrink them even more as they only obtain with smaller and smaller probability. On the other hand, you might be the kind of person who says, look, the fact that I might get this additional 3 utility in the top 80% of states, well, that's worth quite a bit. That's really good. I'm going to weight that pretty heavily in my considerations. The fact that I might get something worth 2 more in the top 30% of the states, again, that's pretty good. That's going to be worth a lot to me. And I claim sort of like either strategy for thinking about how to take the means to your ends is rational. So just knowing the values of consequences and the probability that each act has of leading to them doesn't answer the question of what's the best strategy to get what I want. In particular, some people might prefer the strategy of like going for something that's pretty good no matter what. And other people might prefer the strategy of making sure there's some chance that things are really, really good. And neither counts more as taking the means to their ends. So we can formalize this in a theory that I call risk-weighted expected utility maximization. So in risk-weighted expected utility maximization, the weight of each consideration of the form, I might obtain benefits of a certain size, so I might get like 3 more utils, I might get 2 more utils, I might get 1 more util. The weight of each consideration is up to the individual. He determines how much what happens in the top P portion of outcomes matters in decision-making. So here's the equation. The basic idea is that whereas normally in expected utility, the utility intervals that I've drawn on these figure 2 and figure 3 are weighted by the probability of getting reaching a level at least that high. In risk-weighted expected utility, they're weighted by a function of the probability of getting it something at least that high, which I call the risk function. If the risk function is convex, you're going to look like the graph on the left in figure 3. So as considerations obtain only in a smaller and smaller portion of possible states, you're going to weight them proportionally less and less. If your risk function is concave, you're going to look like the graph on the right. As considerations concern a smaller and smaller portion of the best states, you're going to weight them proportionally more and more. And if your risk function is linear, you're going to be an expected utility maximizer. So this theory is a generalization of expected utility maximization, but it sort of adds in an additional factor. Namely, how much do you weight what happens in the top P portion of states? Whereas expected utility maximization says the weight you give to those states is P. Risk-weighted expected utility maximization says you can give any weight to them that you want. At least, oh yeah, go ahead.
Are you assuming that R of 0 is 0 and R of 1 is 1?
Yeah. So I think I have them on this handout, but I can't oh yeah, okay, it's on the next page. Yeah, so subject to some constraints, R of 0 is 0, so if something's not going to happen, doesn't make a difference in your deliberation. R of 1 is 1, so if something is going to happen for certain, it makes all the difference. R is non-decreasing, so if a good thing is going to happen with some probability, then decreasing that probability can't make the gamble better. You might also add the stipulation that R is increasing. In other words, that if you increase the chance of the good thing, then the gamble gets strictly better, not just that it doesn't get worse. And R of P is between 0 and 1. Okay. So on this theory, 3 things are up to the individual decision maker. His utility function, which measures how much the individual values outcomes, his additive probability function, which measures how likely those outcomes are to obtain. So these are the 2 things that are up to the individual on the standard theory. And third thing, his risk function, which measures the importance of the top P portion of outcomes in the individual's decisions. And we can kind of think of this in one of 2 ways. One way to think of it sort of imaginatively is a gamble is like a distribution of resources to my possible future selves. So when I think about whether I should join the startup, there are like 100 future possible Lauras. One of them gets really rich. 50 of them are like, things are fine, they're not great. 20 of them are in a really bad situation. How do I weigh their interests against each other? And in particular, how do I weigh the interests of the best off future Lauras against the worst off future Lauras? So if I'm concerned with making sure things don't go too badly for the worst off future Lauras, if I want to make sure that if I weight their interests more heavily, then I'm going to have a convex risk function. On the other hand, if I weight the interests of my best off more strongly, I'm going to have a concave risk function. And if I weight them all the same, I'm going to have a linear risk function. Oh, and we're going to call, oh yeah, go ahead.
I have a question. So both strategies you presented were rational with respect to a given risk function. But this assumes that the risk function and the utility function that a person has are consistent with their actual goals. So a common example, since we're talking about the everyday decision maker, most people probably have a pretty greedy risk function. They would rather spend money now, get reward now, not think about their future selves. And a financial advisor sets them straight and explains to them how that will not meet their goals. And otherwise, many people, they have their utility function and risk function, or they think they do, but they end up unhappy and they don't know why. So is it rational? Should we take into account whether the utility function and the risk function align with the goal?
Good. So decision theorists distinguish between 2 notions of rationality, and one we might call the consistency one, and one we might call the reasonableness one. So according to the consistency one, that's like a really thin notion of rationality. It's basically just like, as long as your utilities don't contradict each other, as long as your risk function doesn't contradict itself, you're going to be rational. The one that you're talking about is the sort of more substantive one, reasonableness, and that's usually that's cashed out as like the function matches something in the world. For example, the utility function matches what's genuinely valuable, while it's consistent. In Hume's famous example, to prefer the destruction of the world to the scratching of my little finger, that's clearly not reasonable. Those would be bad values to have. And we can say something similar about the risk function. So I've given you the conditions for having a consistent risk function. I in fact think that the range of reasonable risk functions is more narrow, but it's not, it contains more than one member. So for example, you might think if somebody, so this what I've highlighted is consistent with being a maxi-minner, so being a person that just cares about the worst case scenario. You might think that that actually puts too much weight on the interests of your worse off future self and ignores too much the interests of your best off future selves. So I actually do think there's sort of like a slightly narrower range that's going to be reasonable here. But it's not, but importantly, it's not just the linear risk function, i.e. expected utility maximization. There's going to be some choice in how you yourself make those trade-offs. Does that answer your question?
For the most part, yeah.
Okay.
I guess I'm just thinking, given the option, nobody would prefer their future selves. They would just get stuff now.
Oh yeah, so like future discounting is an interesting case because usually decision theorists talk about like the preferences at a time are like the thing. So in general, yeah, like it's going to be consistent to not care about your future self at all, but we think that would be unreasonable. And I mean, I guess I would also think that people in fact would it's like, this is all about considered preferences. So if your financial advisor tells you like, yeah, you want to make sure you've got some money in your old age, you're not thinking about that. Most people would say like, oh yeah, you're right. So this isn't like rational preferences. You're like preferences here are sort of your considered preferences rather than like the thing that immediately comes into your head.
Just to quickly wrap up. So in the case of the financial advisor, I was actually thinking that most people would say, yes, they want to have money in their old age, but their utility function and risk function, of which it's not immediately easy necessarily to take it to its logical limit and see where it ends up, they will not align with what it is they tell their financial advisor they want.
I get, well, maybe, so I think I'd have to see an example to see that they're not aligning. Maybe, why don't I finish what I have to say, and then if you like have an example or you know, then
thank you.
Talk about it at the end. Yeah, but thank you, that's a really important question. Okay, so I mentioned one way to think about the risk function as like the choice about how to weigh the interests of your best off future self against the interests of your worst off future self. And these selves aren't all going to be actual possible selves. Another way to think about the choice is as a trade-off between two virtues. So we have the virtue of prudence, which is you know, making sure that things go as well as possible no matter what happens. We also have the virtue of venturesomeness, namely making sure that there's some chance that things go really, really well. The risk function represents how you trade off these two goals. And as with many virtues, there are going to be like many ways to trade them off. So for example, consider the virtue of efficiency versus conscientiousness in the faculty meeting. Some people are going to like want to be slightly more efficient. Some people are going to want to be more conscientious. These things pull against each other. They're both like good things, but they in fact conflict. And so you have to figure out how you're going to trade off between them. Or in the case of belief, think about the trade-off between knowing a lot of things and not having any errors in what you believe. These things are in conflict because like the lower you set your evidential bar, the more things you're going to believe, but you're going to have more errors. The higher you set the bar, you're going to believe fewer true things, but you're also going to have fewer errors. And it's sort of like up to the individual in some sense to trade off these two goals. So the risk function is like that. It says, here's this goal in practical reasoning. There are these two things that are in conflict, often making sure things go as well as possible in the worst cases and making sure things have some chance of going as well as possible in the best cases, and each individual has to choose how to trade them off. Okay, and so, right, so we can sort of characterize three states. If you're globally neutral, you have a linear risk function, you're just an expected utility maximizer. If you are what I call risk avoidant, then you have a convex risk function. You're going to display risk aversion, not just in money, but in utility. So of two gambles with the same mean utility value, you're going to prefer the one that's less spread out. A limit case of this is maximin, where you just prefer the gamble with the best worst case scenario. I mean, I'm not sure again whether this is like a reasonable strategy to have. If you're risk inclined, you're going to have a concave risk function. You're going to be risk seeking in utility. So of two gambles with the same mean monetary value, you're going to prefer the one, sorry, of two gambles with the same mean utility value, you're going to prefer the one that's more spread out, that has higher highs and lower lows. And a limit case of this is maximax, where you just prefer the gamble with the highest maximum. So remember our two coffee drinkers who both preferred 1 cup of coffee to a coin flip between 2. Well, on risk-weighted expected utility maximization, we're actually going to be able to characterize the preferences differently. The person who, the first person who just got really jittery is going to in fact have a concave utility function. The first cup of coffee is going to be worth much more utility versus none than the second is versus the first. The person who is just an ardent coffee drinker that likes each cup as much as the last, but still prefers 1 to the coin flip between 0 or 2, is going to be characterized by having a convex risk function. He's going to place more weight on what happens in the bottom 50% of consequences than he does in what happens in the top 50% of consequences. Okay, so we've solved the problem of being able to say what's different about these two coffee drinkers, and it'll be sort of easy to see that we can also capture the Olay preferences. So all you need is a convex risk function, and there's some limits on what the utility function can be, but they're pretty wide. So the idea is that people that have the Olay preference, they have them because they care less about what happens in the best states than they care about what happens in the worst states. Okay, so this is sort of like basic motivation for the theory. Now, one thing that's really important to decision theorists is these things that I mentioned earlier called representation theorems. And so in a standard representation theorem for expected utility, basically you have a set of axioms, as long as, and they're going to be axioms on X, so axioms on things that look like this. So like they're just pairwise preferences. So like, you know, G is better than F just in case, blah, blah, blah. Okay, so if your preferences obey those axioms, then you are going to be represented by a unique probability function and a utility function that's unique up to positive affine transformation, such that you maximize expected utility relative to those two functions. So the theorems are cool because they say, they provide us a way to extract separately your utilities and probabilities just from your pairwise preferences. So happily, I have a representation theorem for risk-weighted expected utility theory that allows us to extract your utility function, your probability function, and your risk function. So we're going to be able to see the separate contribution that your utilities or your values, your probabilities, your beliefs, and your risk function or your sort of attitude towards taking the means to your ends, the separate contribution that each of those make to your preferences. So remember the two coffee drinkers, the idea is if we look at the other preferences these guys have about gambles involving coffee, we'll be able to like, the theory will say that the first guy like definitely has a linear risk function and a concave utility function. The second guy definitely has a linear risk function and a convex utility function. So we can sort of like just see from his other preferences what his reasons are for behavior. So here the theorem basically says there's a set of axioms. If the preferences obey them, then there's a unique finitely additive non-atomic probability function from sets of states to values between 0 and 1. So that's just like standard probability function. There's a unique risk function that's a transformation of the unit interval. And there's a utility function unique up to positive affine transformation. So same thing in the standard theory, such that risk-weighted expected utility represents the preference relation. I'm not going to go through the axioms, although if you like have questions about, like, I'm happy to talk about it if you ask about it. But here's like the basic idea. So the axioms of expected utility maximization turn out to be so strong that not only do they fix your probabilities, they fix your decision weights as equivalent to your probabilities. So it's sort of like, by logic alone, the weight that you put on each state is going to be equal to its probability. But look, even if you think expected utility maximization is like the right thing to do, these two things are conceptually different. So we should at least have a way to like say in our axioms what each of these things are. So, okay, so these axioms are so strong again that probabilities and decision weights are just defined to be the same thing. So here's the idea: weaken the standard axioms so that decision weights are not additive. There are like other theories that do this, if you're familiar with them. And then strengthen the resulting axioms so we don't just get decision weights, we also get additive probabilities. And then show that on the resulting axiomatization, decision weights are a function of probabilities, a function with the above properties. So, basically just like weaken the axioms so that probabilities and decision weights come out of different structures. And then my claim is going to be that the preference structures that determine each of the functions actually shows that these functions like correspond to the things that I was mentioning conceptually they're supposed to correspond to. So the utility function corresponds to like how much you want to include one outcome rather than another in a gamble. In other words, it corresponds to how much you value consequences. The probability function is going to correspond to which event you'd rather bet on. So E gets a higher probability than F, just in case you'd rather the good prize be on E than F. So P is going to correspond to your beliefs about what will happen. And finally, R corresponds to the weight that the best event gets when evaluating a particular gamble. So R corresponds to how much you weight benefits that obtain only in the best states in your decision making. And so I'll just give you a really quick example of how each of these things are determined. And I'll just give, so basically like what the axioms do is they say things like, if you have this preference, then you've got to have this preference too, because those are the preferences that extract your utility function. And so they've got to be the same so that no matter what preferences we look at, we get the same utility function. So I'm going to sort of show you how we get each of these functions from examples of your preferences. And you're going to like hopefully see that utilities really do represent consequences, probabilities really do represent beliefs, and decision weights really do represent how much you care about best states versus worst states. Okay, so let's say, for example, you'd rather have, these are all coin flips, you'd rather have a coin flip between $10 and 150 than between 0 and 170. These numbers are just for illustration. What does that mean? Well, it means that getting $10 rather than 0 in heads is an appropriate trade-off for getting 150 rather than 170 in tails. So those are like, you're indifferent, it means you're like, just that's an equal trade for you. 0 to 10 in heads is an equal trade as 150 to 170 in tails. Let's say you're also indifferent between 110 in heads and 150 in tails, and 100 in heads and 170 in tails. So again, 110 and 100, the difference between those is sort of like you're exactly equal as the difference between 150 and 170 in tails. So if you have both these preferences, then what that implies is that the difference between 110 and 100 is like the same as the difference between 10 and 0. So that's what determines the utility function. You look at when you're indifferent between a trade-off in one context and a different trade-off against the same thing, and then those two trade-offs are going to have the same utility difference. So that's like what utility is according to these theories. And by the way, this is like, this is true in both expected utility and risk-weighted expected utility. These structures will give you that. Although in risk-weighted expected utility, you can only derive this equivalence if the gambles all put the outcomes in the same order. So if like the heads outcome is worse than the tails outcome for all 4 gambles. Okay, so those are utilities. Hopefully that's sort of like, you can see that that really represents how much you value consequences. Would I trade it off in a certain state against some other consequence? That's like how much I value it. Okay, so how do we get decision weights? So let's just say we've already determined our utility function from these trade-offs, and let's say it's linear. Now let's say you are indifferent between 10 in heads and 150 in tails on the one hand, and nothing in heads, 170 in tails on the other hand. Then it looks like you require twice as much compensation in tails in order to make up for a given amount of compensation in heads. So those are your decision weights. So here you place 2/3 of the weight on heads and 1/3 of the weight on tails, okay? Probabilities are going to be determined by which event an individual would rather bet on. So for example, if you're indifferent between heads 10, tails 150, and heads 150, tails 10, then the theory is going to say that your probability of heads is equal to your probability of tails is equal to 0.5. So this is how probabilities are determined. Hopefully you can like see that probabilities very clearly represent beliefs about states of the world, like nothing to do with money. It's just which event would you rather put the good prize on versus the bad prize. That's how probabilities are determined in risk-weighted expected utility. And finally, the risk function is determined from the decision weights of best events with particular probabilities. So we've already gone through, we've derived our utilities, our decision weights, and our probabilities. We just set the risk function of a given probability equal to the weight of some event with that probability when that event is the best event. So from the above, we can derive that the weight I put on the top 50% of states, I find something that I give probability 50% to, okay, heads and tails. I figure out how much weight it gets when it's the best state, 1/3. Okay, so the risk function of the top of 0.5 is going to be 1/3, indicating that I put weight 1/3 on the top 0.5 states. And the axioms are basically fix that anytime you derive these values, they're going to be consistent. So it's not as if like looking at one gamble, I'll get R of 0.5 is 0.6 and a different one, it's 0.7. No, any way of performing this procedure, you will get the same value. So that's what the axioms do. They give you a consistent, these 3 functions, and they give you unique of these 3 functions. And so this is like basically how they work. And I hope that you can sort of see from these structures that like indeed these 3 features of preferences like really do represent the things I'm saying they represent. Okay, so finally, I'm not going to be able to argue in detail, but I'm just going to give you like a little taste. I've been so far describing the theory. I've been claiming that anyone who obeys this theory is rational. That means I have a wider definition of rationality than the standard theory because I say, for example, someone with the LA preferences, that person is rational, but the standard theory is going to say they're irrational. So the way I'm going to show or argue that risk-weighted expected utility maximizers are rational is basically I'm going to take all the arguments that have been given in favor of expected utility maximization and argue that they're mistaken. So obviously a big project, is why it takes a whole book, but I'll just like give you a flavor of these arguments. So the first argument we've just seen is this argument from representation theorems. The argument here, if all you have is the EU representation theorem, then the argument is like, look at these axioms, they characterize rational preferences. My reply to this argument is going to be that actually the weaker axioms of risk-weighted expected utility are better supported as rational requirements. Another way to put this is that one can have a non-linear risk function without being inconsistent in how you value and how you make choices across different acts. And we don't just have to look at the sort of details of the theorem to see this. We can hopefully see it in, hopefully I've convinced you that this actually is a feature of means ends rationality. This is like a choice you have to make. How much do I want to trade off what happens in worse states against what happens in better states? And I can make that choice consistently without needing to put equal weight on all states, regardless of whether they're the best or the worst. Okay, maybe I'll just mention these other arguments since I know we're nearly out of time. So there's a very popular argument for expected utility theory comes from the sure thing principle. And this is a principle that basically says if two acts are going to give you the same result, on some states, no matter what, just ignore those states in your decision making. In fact, this forms an argument that having the Allais preferences is irrational. Well, okay, maybe I'll just you can ask more about this in Q&A. Basically, this principle appears to be kind of weak, but it's actually pretty strong. It says not only that you have to value things consistently, but that you have to weigh your reasons the same in different contexts. And you might think you don't have to do that. So anyway, but I know that's a little sketchy, but happy to talk about it more. Finally, or third, there's this argument that over time, the risk-weighted expected utility maximizer is going to make plans, but fail to carry them out. For example, reply, well, no, he's not going to do that. And in fact, there are several strategies he could adopt that are all consistent with having agency over time. And finally, the fourth argument has to do with repeated choice and the idea, and this is not a popular argument for expected utility maximization now, but it actually was when it was first invented in 1700s. The idea that you will do better over the long run if you maximize the expectation of the thing you care about, rather than say the risk-weighted expectation. Reply, well, actually thinking about repeated choices changes the problem in relevant ways. Repeating the choice eliminates the risk. So thinking about how you would behave if a choice was repeated over time is not the correct way to figure out what you should do if you face a choice once. And that's why, for example, the person who puts more weight on worst case scenarios will behave pretty similarly to the person who puts more weight on best case scenarios if, for example, they're playing the stock market or playing a game of poker, because that consists of a lot of choices that over time eliminate the risk. But the person who puts a lot of weight on the worst case scenario versus the person who puts a lot of weight on the best case scenario are going to make really different choices when it comes to, say, their careers or who to marry or where to live, these kinds of choices that you can only make once. So, the risk, assuming he doesn't have a ton of chances to do lots of new startups, the risk avoidant person is going to stay at his job. The risk seeking person is going to go out to the startup. Neither will be swayed by the thought that if they were to face this choice over and over and over and over again, they should do a certain thing because they both only live once. And in fact, both are rational. All right, well, I hope I've shown you an alternative to expected utility maximization that captures this, this feature of ordinary decision-making, this feature that has previously been overlooked. We can do the same mathematical things with it, namely we can derive your values and beliefs from your preferences. And in fact, I think we can do something better. We can derive your beliefs even in cases in which your beliefs, your decision weights are not equal to your probabilities. And we can sort of see which structures of your preferences are related to each of these three functions. And as well, there are lots of different settings of this new this new function that will make you rational and indeed will make you reasonable. All right, that's it. Thanks for listening.
Well, very nice, very nice. I do have a couple of questions, and there is someone who has a question that Shateldon, right? Could you go ahead and speak? Let's see, where is she? Disappeared.
Rohit, I also have a question.
Go ahead.
Okay, so let me first preface by saying that I don't know anything about decision theory and mathematician. And so I read your paper, 2017 paper, summary paper, to get some idea about your talk. And so the question I have is mathematical. The expected utility is the integral or summation of probability times the utility, right? And then you have this function, and this function you're applying essentially to the first factor, the probability, because you cannot apply this factor directly to the probability because then it won't be a probability function. So you apply instead to the cumulative distribution function.
Yes.
It still remains a distribution function. If you take its difference again, you get back to the modified probability, right?
Correct.
But instead of applying the risk function to the probability function, you can also equally well apply to utility function, second factor.
So I mean, that's essentially what that. So if you sort of started that over, but talked about taking the expectation of probability times money, and then took the cumulative distribution function, and then noted that you could apply it to either probability or money. Basically, the risk function is when we apply it to probability, and the utility function is when we apply it to money.
So there is some more. I also read your 2016 paper, which is the reply to Pettigrew. And there you do this, what you described today. And then both Pettigrew and you try to somehow interpret it as a modification of utility function. So I was wondering, instead of trying this laborious process and getting all kinds of difficulties, why not directly modify utility function, which is much easier?
Well, you get different results about which preferences are going to be rational. So for example, you could not simply modify the utility function and recover the Allais preferences.
Can you say it again?
So you couldn't modify the utility function and recover the Allais preferences. You couldn't get the, on the handout on the bottom of page 1, L1 is preferred to L2 and L4 is preferred to L3. You couldn't recover those preferences by modifying the utility function.
I mean, I reworked the examples you have in your paper, applying the risk function you have, utility function, and I got very similar results.
Can you give an example? Because the risk function is
the square root and a square.
Okay, so can you give me an example? Can you recover the Allais preferences for me? Because it ought to be provably true that there's no utility function or modification of the utility function according to which L1 is preferred to L2 and L4 is preferred to L3.
Well, I have to work it out.
Okay, yeah, so if you work it out, you should see why it's not going to give you the same results. Yeah. So it's possible that I misunderstand your question, and then you can say, oh, here's how it would go, and then I would, and then we could talk more. But the basic idea is like, sort of modifying the value of something is going to give you different possible configurations of preferences than modifying the way that the values get. And you're right, you can get something very similar. So for example, take risk aversion in money, which formally means you disprefer mean preserving spreads. So of two gambles with the same mean monetary value, you don't want to take probability and spread it outward. Now, as it turns out, this can be accounted for either by the risk function or the utility function. So like you can often get a lot of the same preferences, but you won't be able to get all the same preferences. And importantly, we can see from the axioms that like the two functions like correspond to really different things, or like intuitively really different reasons you have for your preferences.
So, okay,
Yeah, go ahead.